Hello, this is David Wong, and here's another video that was requested by many people on exactly how the zkBitcoin repository is organized and structured, and also sort of how the zkBitcoin white paper specifies the protocol and how it works. So maybe I can go through both at the same time, but I'll start with the paper. The paper is actually quite short, 19 pages, but the font is not, it's kind of big, and the margins are big, so don't let that fool you. I just like pretty documents, and so this is my setup. But the introduction, as usual, is kind of useless. You can skip it if you have context. And then related work, which sorts of talks about different projects, but most of what we saw were projects that were adding an opcode on Bitcoin to verify proofs, which we didn't want to do because we think it's kind of hard to do with Bitcoin, as the project is quite ossified, and changes like that usually tend to turn into forks, hard forks. And the other one that's interesting but doesn't use ZK proofs, but could potentially support verification of ZK proofs, is the BitVM project that uses fraud proofs to execute circuits, binary circuits, or maybe more than binary circuits, maybe with more customized gates, more efficient gates as well. But this one is quite, is still quite limited, and especially the fraud proofs are split between many transactions, and it's something that we see as unrealistic at this point. It's more of a curiosity, and it's amazing work to be able to come up with a scheme like that. But it's so complex that we didn't think it was really worth implementing it and using it. And so anyway, we came up with this zkBitcoin protocol, and the overview basically says it all. It's the project is basically an L2 that supports two types of zkapps, what we call zkapps, these zero knowledge circuits or applications or smart contract, whatever. The stateless one and the stateful ones, and I explain exactly how they work. I've already introduced the difference between these two types of zkapps in my previous video, so if you don't know that, then you can check that out, but I'm not going to re-explain that. And the secret here is that let me see if there is if I can find a diagram. The overview is very high level, but the section 4, the zkBitcoin protocol, has pretty good specifications of the actual protocols. So maybe let's walk through that. But just as a reminder, we're in the case where we're in more of an L2 kind of situation, where we have a committee of some size, let's say n participants, and they collaborate and they manage a wallet. As long as a threshold T of these n participants are alive and being honest, then they can collaborate to sign a signature to unlock funds from that wallet. And so stateless zkapps, but we'll see that stateful zkapps are not too different, are basically hosted under the wallet of this collaborative wallet between these multi-party computation participants. And specifically, we use the Frost threshold signature scheme, which is a threshold signature scheme for Schnorr signatures, which is supported by the Bitcoin Taproot update. And we use the Zcash library, which is really good, and has been very useful. So anyway, let's look at stateless zkapps. So we always use the rules of Alice and Bob. Alice deploys zkapps and Bob uses them. It's kind of arbitrary, but it's easier if we have these characters. And basically, Alice, when Alice wants to deploy a zkapp, a stateless zkapp, will just create a transaction that will send some funds, the funds that she wants to lock, under that zkBitcoin address. And that will be one UTXO, one output. And then she will create another UTXO, which is an unspendable UTXO that will contain some data. and the data will be the digest of the verifier key of the circuits that she wants to use. So usually I say it's just a hash of the compiled circuit, but technically it's really a hash of the verifier key, only the part that allows you to verify circuits and not nothing else. And this is all we need to verify some proof that was proof of execution of some circuits. So the transaction actually looks like this, where these are standard stuff that are in a transaction, and basically Alice funds that transaction with some inputs. We don't really care, and in the outputs there can be a number of outputs, but a zkapp transaction will contain at least these two outputs. As I said, some value being locked under a script pub key that actually locks this value to the zkBitcoin public key, and we use a pay to taproot script, as the zkBitcoin public key is a taproot key. And we also have this UTXO that's not spendable, and that uses a script that's an op return followed by the verifier key hash. And so that will authenticate exactly what verifier key or what circuit is locking these funds. Okay, now we look at Bob. So Bob wants to spend these funds. Remember, a stateless ZK app is really a use once ZK app. It's a single use ZK app. So what they do is they produce a request that they will send to the L2. So the request, to perform that request, we need the actual verifier key. And so this is needed to actually verify the circuit. This is let's say a compressed version of the circuit that verifiers can use. So of course here we only have a digest, so we need the real verifier key. And you can think of it as the circuit, but it's a bit less than the circuit. It's smaller, and you can't really recover the circuit from that alone. So the verifiers, this multi-party computation in that L2 doesn't really know what the circuit is. So that's also interesting. And then they produce a transaction that spends that UTXO specifically, right? The value is locked here, so they create a transaction that spends that. And they also produce that's as input, right? And we also expect an output, which is a fee paid to the zkBitcoin fund. We don't really know. I'm not sure what I set the fee at. It doesn't matter. It's a testnet for now. But we have a fee. And everything else, all the outputs are free. You can do whatever you want with your transaction. And we rely on the fact that you have a Bitcoin node with some wallet set up somewhere locally or on some URL, on some IP, and it's on you to fund your transaction and to do whatever transaction you want. And finally, of course, you want a proof of execution that we will be able to verify using the verifier key, right? That proof is of a circuit, right? The verifier key circuit, I guess. And the only thing we request or we require is that the circuit has a public input, which is called truncated transaction ID. And basically this is here so that when Bob sends that request, actually I have an actual example of a request that I'll show you after. But when Bob sends a request, we don't want a malicious node on that layer 2 to be able to steal that proof in the request and then use it for their own transaction to spend the zkapp to their own UTXOs. So the proof will actually authenticate the transaction that spends it. So that's an interesting facet of the protocol. So the MPC sees the request, it validates the request. Basically, the proof will be verified. I'll go more in depth here, but the proof will be verified, and we'll make sure that the verifier key to verify the proof is also the correct verifier key according to the hash that was posted here in that UTXO. Okay, and basically if the Oh yeah, oh yeah, the transaction that just as a recap, the transaction that Bob produces again has any inputs, but one of the input has to be the zkapp, which is a zkapp is referred to by its transaction ID and the index of the outputs. And here we don't have anything to actually spend it yet because this is Bob doesn't know how to sign it basically. It needs to rely on the layer 2, the MPC committee. And then in the outputs, they have to pay one of the UTXO is to the zkBitcoin fund, and it has to be of some specific value. And any other outputs, of course, is controlled by Bob. But that's basically it. As soon as that transaction is, signed by the committee because they can verify that the proof is correct, then Bob can send it broadcast it to the network and get it on Bitcoin. And the interesting thing is that the committee doesn't really need more than this transaction and the verifier key that's contained, that's authenticated by the zkapp transaction ID, and a proof that verifies for that verifier key. That's the only thing that the committee needs. They don't need to access Bitcoin. They don't need to check anything on the chain. Actually, these UTXOs might not even exist on the chain. The committee doesn't care. As long as they see something like that, they will sign it. It might actually be a transaction that zkapp might actually have already been spent. It doesn't matter. The committee will sign that anyway. So the committee really has no clue about Bitcoin. They will just sign requests that look valid to them. And basically the first person that proves that they can spend a zkapp will be able to spend it. Whoever can spend it later on will not be able to spend it because they will already be spent, right? The UTXO will not be valid anymore. Okay, let's look at a stateful zkapp, and then I'll show you what a Bob request looks like. So a stateful zkapp is basically the same thing, except that when Alice deploys that zkapp on Bitcoin, they don't just include the digest of the circuit. They also include the first state, the initial state. And that initial state, because of the limitations of Bitcoin, is a single field element. We wanted to have more field elements, but right now it's only one single field element. So we presume that most stateful zkapps will use a digest here, and they will deconstruct that digest by providing a preimage as witnessed in the circuit. But it's important that this field element is posted on chain, because like that, if someone else wants to use it, they can actually see that field element. And yeah, here I explain why we only use one field element. And the transaction that Bob, oops, what am I looking at? Oh yeah, that's the transaction of Alice. It should look exactly the same as the previous transaction, except that this script pub key uses an up return to push not only a VK hash, a verifier key hash, but also the initial state. And now when Bob wants to use the zkapp, the stateful zkapp, that's when it gets interesting. They will, same protocol as before, but this time one of the outputs will have to be another zkapp, right? Because we don't consume the zkapp now, we just move it to another transaction ID, basically. So whenever you use a zkapp at some transaction ID, it will create an updated zkapp at some other transaction ID with the same verifier key, but potentially with a different state, as the state can be updated. And now we have more public inputs. Of course, we have the truncated transaction ID. Same issue here. We want Bob to authenticate the transaction that spent something so that nobody can front run him and spend it before him. But we also have a few other public inputs. We have the previous state, the new state, although that's kind of a public output more than a public input, but in ZK it's kind of the same. And we also have two other fields. We have the amount out, which is the amount that you want to withdraw from the app. And so the amount of that's locked in the new zkapp will decrease by this amount. And if you want to deposit some Bitcoin in the zkapp, we will also increase the amount of the new updated zkapp with this amount in. And here it's missing a space. We should really correct that. But otherwise, everything remains the same. And yeah, this is the public inputs, but we don't really care about that. I just explained that. And yeah, so this transaction that Bob creates to spend that that zkapp UTXO is the same, but now not only we have a fee, we also have a new zkapp in that transaction. So again, a zkapp is a value being locked to the zkBitcoin taproot key, and another UTXO that's unspendable that contains a hash of the verifier key, the same one, and the updated state. So hopefully that makes sense. And here, of course, the MPC committee, when they verify the proof, they need to verify that this transaction is well formed and that the VK hash is the same as the previous one, and that the new state is the one that's contained in the public input, the new state here. And if and this is authenticated by the proof. When you verify the proof, it will tell you indeed this is the new state after updating it from the previous state. Okay, so I guess this is the specification not of the zkapp level, but more of how the MPC works. And here we also have the same characters. We have Alice and Bob, but now we have the MPC members, or we have n of them with t the threshold that's necessary to make it work. Meaning that if there's not enough participants that are alive and being honest, then the protocol might just not work, or worse, people might be able to steal funds from the protocol. And finally, because every message in this multi-party computation is a broadcast, we can have an orchestrator that will basically sort of be the front of that scheme. And when you send a message as Bob to unlock, or a request to unlock some funds or use a zkapp, Bob will not send that to the committee themselves directly, but will send it to the orchestrator. And the orchestrator is the only one that knows the IPs of the different committee members, and will send that to the committee members, and we'll go through 2 rounds of that Frost threshold signature scheme, and basically collect a bunch of messages, send it again through another round, the second round, to all of that committee, and then collect the final signature that they can process. So, okay, so now I go through the protocol. Basically, Alice doesn't interact with the service, so we don't explain that here. But only when Bob interacts with the orchestrator, they send that request, and so we have the request here. Very briefly, there is the transaction that Bob wants to get a signature on to spend a zkapp. There is the actual zkapp transaction. We need these because, again, the MPC committee doesn't have access to the blockchain, the Bitcoin blockchain. So they want to make sure that the UTXO that this one spends as inputs is the hash of an actual transaction that contains a zkapp with a verifier key hash. This actually doesn't exist anymore, so ignore that. Someone contributed a PR there to. I don't have the name of that person, but thanks again to remove that. The actual verifier key, the proof of execution for that verifier key, and finally an update, potentially if in the case where we have a stateful zkapp. If we don't have a stateful zkapp, then there's no update. We just consume the app. And and we need something, the previous output, this is just something that the signers need to be aware of, and that's more of a specificity of the Bitcoin protocol and how you're supposed to sign UTXOs that you want to spend. And an update in the case of stateful zkapps is really just basically all the public inputs that we're going to use. The update takes a previous state, and goes to a new state, and also tells us exactly how much Bitcoin are being withdrawn and how many Bitcoins are being deposited. And there's a truncated transaction ID. Here we skip that, meaning that the MPC node will recompute that themselves from the transaction that Bob is sending them by hashing the transaction and truncating it, because it doesn't fit in a field element without truncating it, and we'll provide that as public input. And then basically the orchestrator will forward that request to the MPC nodes. There are two rounds to a signature. So the MPC nodes have an endpoint called round 1 signing, and another one called round 2 signing. But basically the orchestrator sends a message to everybody during round 1, waits for enough answers, then collect these answers in a package and sends that package to everybody, all the committee again. The committee responds, the orchestrator collects the responses, aggregate them into a signature, and sends that back to Bob. If that's not clear, you can go through the paper. That's what I explain again. That's what we explain again. I guess there's another particularity of the MPC, but they keep track of tasks because the protocol is not stateless. You have to remember what you did in round 1 to be able to go through round 2. The MPC committee keeps track of each signing task in a local signing task structure. And a local signing task is just something that you create after round 1, at the end of round 1, that says we had a proof that verified, and that was the hash of the proof, for that smart contract, that zkapp, and basically it's a structure that contains the zkapp, and it was for that transaction. This is the stuff we need to sign, and I'm not going to talk about that. And these are the nonces that we produced during round 1. And basically, this is secret data that is needed to go through round 2 once we go to round 2. Because the stuff we created during round 1 are mostly commitments. And since we have multiple local signing tasks that can happen at the same time, we keep track of them in a hash map. So anyway, I'm talking about the response here, but it doesn't matter too much. We're sending commitments, and here what we save are really the commitments, but also what is being committed. So some secrets. And what do I explain here? I explained some stuff about what if it stops at round 2, or what if several round 1 for different proofs arrive, what to do, and I sort of explained that these are not issues. This is what happens in a round 2 request. Basically, you need to remind the MPC node you're talking to what transaction ID we're referring to. What's the proof hash, because we might be, we might have several requests to spend the same zkapp but with different proofs. And then the aggregated messages from round 1 of all the participants, and then the actual message to hash. And so I believe I don't remember why I included that, but if I remember correctly, this is just to make sure, because the MPC nodes will recompute that. It's here just to make sure that if the MPC node, recompute that message from the transaction and get something else than what the orchestrator got, then there is an issue and they will abort. And then they will respond with their signature share, and that the orchestrator can collect all of these shares and add them up together, and that will produce the signature. And then they send they insert the signature in Bob's transaction, and they send it back to Bob. And I say here that it's the responsibility of Bob to send it to the Bitcoin network. So if we go through the paper, maybe I can sort of ignore these sections, but we had some issues making Frost work with Bitcoin Taproot. Maybe very briefly I can explain the issues. But Bitcoin Taproot Schnorr signature standard basically drops the y coordinate of an elliptic curve point, meaning that you only see the x coordinate. The problem is that usually in this sort of compressed format, because it's smaller than having two coordinates, you have one more bit that tells you if the y coordinate is even or odd, for example. Because for every x coordinate, you can have two y coordinates. So we can recover the real elliptic curve point behind an x coordinate. But usually we need a bit more indication because there are two potential solutions. What Bitcoin does is that it always assumes the y coordinate is even, if I remember correctly. And so when we do Frost and we do an MPC, we might actually generate, for example, a public key y that actually has an odd y coordinate. And this is actually true for different things that we collaboratively create at different stages of this collaborative signature. And so I sort of explain in this diagram all of the different edge cases. And I explain that the y is the public key here, can have different y coordinates. So we have to sort of correct the private key or the private key share, since there is no private key, but instead every MPC node has a private key share. They all have to correct it and negate it in the case that they generated a public key that has an odd y coordinate, because in reality they have a public key that has a y even coordinate, and so they just have to negate their private key basically. And the same can be true for the tweaked public key. I'm not gonna talk about the tweaked public key here, but basically Bitcoin uses public keys and tweaked public keys. And so we have that edge cases also, and during the signature we also produce this commitment R during the round one, and this commitment R is an elliptic curve public point, and the same prime is true here. Everybody has a share of the nonce K that produce an R, but if the R they produced has an odd y coordinate, then they have to negate their share of the nonce. And it keeps happening throughout the protocol, and that's something we had to make it work. And then there's some security considerations. It's a pretty short section. Maybe we should have written more, but it basically restates whatever I just told you, that the protocol relies on the MPC committee, and they don't need to know about Bitcoin and so on. And then we talk sort of about future work and some other things, but basically right now we only support 2 to the 16 or 2 to the 17, I don't remember, constraints, but this is something we can easily increase. And we also only support Circum and Snark.js, but we want to support proofs that are made with Gnark, for example, or Kimchi, or Stark and Cairo, and it'd be interesting to support different proof systems, and this is something we can do pretty easily. So anyway, I guess this is a walkthrough of the paper, and I'm gonna stop here. And I think at this point I should probably make another video on the actual implementation, because I've already talked for quite some time. I thought I would be able to do that faster, but I apologize if you were hoping for a shorter video. And hopefully that made sense. I didn't want to spend too much time either. But yeah, let me know in the comment of the video if you have any questions, or you can create an issue on this repository if you have a question, or if you want to contribute. And I guess look forward for my next video, where I will spend more time with the zkBitcoin repository.